Defining new bijections from old bijections. Cartesian product of a countable infinite set with itself.
Let's start proving the following exercise. Let's show that if we have two sets A and B such that the cardinality of A equals the cardinality of B, then it's also true that the cardinality of A cross A equals the cardinality of B cross B. Remember that the fact that cardinality of X equals cardinality of Y means just by definition that there is a function f from X to Y such that f is bijective. You can show easily that this is an equivalence relation. So let's prove this fact, the exercise. First, since A and B have the same cardinality, then by definition we can fix some bijection f from A to B. It doesn't really matter if we take f from A to B or from B to A, because the inverse of a bijection is also a bijection. We want to show that A cross A has the same cardinality of B cross B. And in order to do that, we need to find a new bijection. So we need to find some G going from A cross A to B cross B. That is bijective, meaning one-to-one and onto as well. So we need to define this G. There are several ways to do this, but the most natural way is the following. We define a G from A cross A to B cross B by G of xy equals to f of x, f of y. This makes sense because the values of f land in B. So this is a well-defined function that sends pairs of elements of A to pairs of elements of B. Now let's show that G is bijective. So to show that a function is bijective, one shows that it's one-to-one, and then that it's onto. Let's do one-to-one first. So we need to take two elements in the domain of the function. Let's call these elements x, y, and x prime, y prime. So they are ordered pairs. And then let's assume that G of these inputs equals to the same output. So we assume G of xy equals G of x prime, y prime. So by the definition of G, this means that f of x, f of y equals to f of x prime, f of y prime. So this is an equality of order pairs, which just means that the first components agree and also the second components agree. Now f is a bijection, so in particular f is one-to-one, and that allows us to conclude that x equals x prime and y equals y prime. So here we're using f1-to-1 two times. And then we assemble this pair again. So we get x comma y equals x prime comma y prime. This finishes the proof of 1-to-1. Now let's prove that G is onto. to start with a typical element in the codomain, which is in this example is b squared, or b cross b is the same. So let's call this p comma q. We want to show that there is some a comma b in a cross a, such that the function maps a comma b to p comma q. And since f is onto, actually there is some a in a mapping to p, and similarly there is some b in a mapping to q. So here we use onto 2 times. So in conclusion, a comma b as a pair belongs to a squared, and then we compute g of ab. So by definition of g is just like f done twice. So g of ab is f of a, f of b, which is equal to p comma q. And this finishes the proof of onto. So in conclusion, the function g is bijective. And this is the end of our exercise. Now we want to see the Cartesian. We want to analyze the Cartesian product of a countable infinite set with itself. So we just proved in the previous exercise that whenever you have two equinumerous sets, A and B, then the cross product of A with itself is equinumerous to the cross product of B with itself. Remember the notation, A squared equals A cross A for every set A. We're going to use another fact here, that it's just that n cross n is countably infinite. In other words, the cardinality of n equals the cardinality of n cross n. We'll leave it as an exercise, but this is a well-known fact. And now our final theorem for this video. It says that if you start with a countably infinite set, and you take the Cartesian product of that cell with itself, then that set is also countably infinite. So this is a preservation theorem. You can start with a countably infinite set, take the Cartesian product, you will end with a countably infinite set. So Cartesian product does not increase the size of countably infinite sets. So the proof, we start with a countably infinite set by hypothesis. So by the previous exercise, the cardinality of n squared will be equal to the cardinality of b squared. That's just because the cardinality of n is equal to the cardinality of b, by definition of countably infinite. So we fix a bijection between n cross n and b cross b. Let's call that bijection f. Now by the fact above, which we didn't prove, we can fix some bijection g from the one-dimensional naturals to the two-dimensional naturals, namely from n to n cross n. So far we have the following picture. It's a diagram between three sets, n squared, and b squared. And so far we have two bijections. We're going to take the composition of these two bijections, which is f composed with g from n to b squared. And then it's easy to see that composition of 1 to 1 is 1 to 1. Composition of onto is also onto. So composition of bijections is bijection. So the fact that f and g are bijective implies that h is also bijective. We'll leave this as an exercise. So in conclusion, cardinality of n equals the cardinality of b squared. So by definition, b squared is countably infinite.